Alright, so welcome everyone to Sims Academy. Alright, so basically we're going to be continuing from where we stopped. We're looking at the Aspen Plus process simulation training. Alright, and then for this particular session, we are going to be looking at the production of ethanol. Alright, so we're looking at ethanol production, which is model 2.1. Alright, so remember we are actually doing the process simulation training itself. I started working on different units and streams and some other things. All right, so basically now we're looking at ethanol production. All right, and then we have a problem statement. Now in this particular production process, we have been tasked to build a simulation to produce ethanol from corn using fermentation. All right, so the corn starch is in the form of sugar, which is glucose in water solution, is fed to a fermenter along with yeast to produce ethanol and byproduct CO2. Alright, so the fermenter product is produced in two stages of degassing to remove most of the CO2 produced. The liquid product is fed to a distillation column to remove the water and concentrate the ethanol product. Alright, so going to our process description. Alright, before we move on, I just need to let you know that we are not going to be making use of the yeast in this particular simulation. Alright, so we're just going to be focused more on the production of the ethanol and the CO2 from our glucose, but we're not going to be looking at the yeast. Alright, the yeast usually used to serve as a catalyst, but we're not making use of it, alright, for this particular simulation. So let's go. Alright, in this fermentation section of the corn to ethanol process, a glucose in water solution is fed to a fermenter along with additional water stream for concentration control. So basically we are mixing our glucose. Remember, our glucose is representing the corn starch, all right, and then it's in water solution, all right. So and then it's being fed to the fermenter or where it undergoes fermentation, and then water is also sent into that fermenter to help with concentration control. Alright, so remember we are not making use of the yeast, but we say the yeast is separately added. So if you're supposed to do it properly with the addition of yeast, you're supposed to be adding the yeast to your fermenter. Alright, so the fermenter product is first degassed in a single stage flash drum to remove most of the CO2 produced from the fermentation. Alright, so let's stop here and let's quickly proceed to Aspen Plus, and then as we go on we continue. Alright, so let's go to Aspen Plus, but before we do that, let me quickly go over the diagram. This is the process flow diagram. This is what we're trying to achieve on Aspen Plus. Alright, then we have our parameters. So the first thing is our components. Alright, so we need to get our component right. We're making use of ethanol, water, glucose, and CO2. Alright, so let's go over. Alright, so here in Aspen Plus, we select our components. So we're starting with ethanol. We have water. We have glucose. And then we have CO2. Okay, so the method we're supposed to be using for this is the NRTLRK. So under the base model, I pick my NRTL, and then I can change the method name to this. Alright, so for my Henry component, I click on this, come here. Alright, because the Henry component was required for us to use CO2, so I select CO2 and I am done with this. Alright, let's go back to the question so you see it. Alright, so you can see where we have Henry component CO2, property method, NRTLRK. Alright, so moving on. Alright, Alright, so from here I click on next. Analysis. Alright, so let's go back. Click on next, then I can run it now. Alright, so results are available. So the next thing we're going to be doing is to go to the simulation. Now, what we saw there before was just like the interaction between ethanol and water, the binary interaction. Alright, I think I've explained that to the students already on YSIMS Academy while they're going to training. So let's go to alright, let's go. So we have two feeds. We have two feeds. Alright, so one is the fermentation feeder. So let's just get to the diagram and see the name given. Alright, ferm feed. Alright, fermenter feeder. Oh, sorry, fermenter feed. And then this is what it contains: glucose and water. And then we have the water feed. So let me just give the name. Let me just give the name. So this first one is ferm feed, and then this one is water feed. All right, so for this particular one, let's start with the ferm feed. So we have the temperature at 80, change it to Fahrenheit. We have the pressure at 20 psig. Okay, then we are having the composition as mass flow. Remember, this is pounds per hour that is given, so we change it to mass flow and then change this to pounds per hour. All right, so basically we can just put in our composition here, the mass flow here. So we have water to be 255,000. All right, that's 255,000. And then we have glucose to be 85,000. All right, so after doing this, you can see that it's showing the blue tick. All right, showing the blue tick. You can close this. Just come to this place. Let's go to the water feed. So at this point, we have 80. Still making use of 80 Fahrenheit. Our bar is 20 psig. That's the pressure. Pressure is 20 psig. And then we are also having the mass flow. Changes the mass flow in pounds per hour. Okay, and then for our water, remember we are adding extra water for concentration control, so we put in 32, okay, 320,000. So let's look at what we have in. All right, so we can see that we are in line 80 80 80 20 psig. Okay, this one is for mass fraction. All right, so let's quickly do that. According to what we have there. So let me change this up. All right, so according to what we have there, they put the mass fraction of water. Although this is correct, this is right. All right, but just to do what we have in the question, change to mass fraction, put this as 1. Can come here, change this to my mass flow, and put in my 320,000 right here. So it's basically the same thing. Two processes are the same, still going to give you the same result. All right, so having done that, then we bring in our fermenter. Now we're making use of the R stock. For this, you come to reactors, make use of this. All right, so this particular reactor, this particular reactor here is a stoichiometric reactor based on fractional conversion and extent of reaction. So I'm going to be showing you that in here. Okay, so come to reaction. Okay, you can, oh, it's not showing here. All right, let me quickly add what we need to add for this. All right, so now let's check the operating conditions for our fermenter. All right, so for our fermenter, we are working with 110 Fahrenheit, working with 0 psia, and then this is our reaction. That's glucose equal to 2 moles of ethanol to give us 2 moles of CO2. All right, the reaction conversion is 1.0. Key component is glucose. So let's get back. Let's get back. All right, so temperature is 110 Fahrenheit. And then we are having the pressure of 0. So that means no pressure drop. That's what it implies, no pressure drop. So basically, it's still the same pressure from the feed that is coming in here. So no pressure drop. Now let's go to reaction. So at this point, okay, I need to put my, not connected this yet. So I need to connect them. 1, 2, let's align this. Okay. All right, so we need our product stream. Okay. Now I can go back and then create a new reaction. All right, so you saw that this didn't come up because of my R stock wasn't complete. All right, so I didn't add the streams, the material streams, both the inlet and the outlet. So that's why that didn't come up. So the component we're having first is glucose, and then we are having ethanol and CO2 as the product. All right, so basically most times when you are doing anything reaction, both on Aspen plus and Aspen ICs, all right, so your reactants are usually negative and then your products are usually positive. That is the way you specify them. So for this one, I'll put in 1. Once I put in 1, it changed to -1. That's to represent my reactant. And then for this other 2, put in 2, and then it just remains the same as 2. Now, we talked about the molar extent, we talked about the fractional conversion. All right, so for this particular question, we're making use of the fractional conversion. All right, and then it said we can make use of this, it's 1, and then the key components. All right, fractional conversion of glucose. Remember, it's glucose. This fractional conversion most times is usually from your reactant. All right, you can usually just select a reactant, and then we are saying that we want the glucose to be totally transformed. All right, the reaction process is using the whole glucose to produce ethanol. and CO2. That's basically what we just specified with this. Alright, so having done that, I can close this, and I can run first. Okay, let's wait. Okay, so we're having results available, so I can just check what we have. Come to stream. Alright, so in S3, remember S3 is our product stream. You can check the mole flow. And I can see that my glucose, which was 214, that's the inlet from the FEM feed, alright, it was converted, totally converted. Remember, that's what we specified. And then now we are having 420 moles or 428 kilomoles of ethanol being produced, and we are having glucose at same thing too, so 428 for CO2. Alright, so having done this, now the next thing I need to look at is, let's get back, I was supposed to degas. Alright, so I'm supposed to be adding a flash drum to this. Let's just look at what we have in the question. Alright, so from here you can even see we're supposed to degas. That's the first degas. From the description, it said that the fermented product is first degassed in a single stage flash drum to remove most of the CO2 produced from the fermentation. Alright, so what we just need is to get our specifications for the degas. That's 0 pressure drop and 90 Fahrenheit. Okay, so let's go back. Alright, so from here, just need to add the separator. Okay. Okay. So these are the product streams we are looking at. Alright, so remember the operating condition. Still have 0 pressure drop, we put in 0 here. Yes, don't mind it. Anytime you put 0 in your pressure drop, it's just automatically specifying that it is 0 pressure drop. Alright, and then this was supposed to be working for 90 Fahrenheit. So let me confirm that. Yes, 90 Fahrenheit. Okay, let's add the pump to it and then we move and wait till the next video. Alright, so let's add the pump. Okay, let's show you where the pump is actually for the liquid coming out from the degas. Alright, so remember this is it, so this is the pump we're trying to add. So we have CO2 and then we have to pump, we have frame out. Alright, so let's quickly run this specifications. Okay, alright, so we have, okay, we have 90, which has been done already, and then for the pump it's running at 100. Okay, pressure increase to 100. Alright, so let's get back to our simulation environment. Alright, so this is your specifications for the flash drum. Okay, so having done this, this is supposed to be CO2. This is, let's put frame out. Alright, and then we have to pump. Okay, so after doing this, the next thing we just need to add, alright, is the pump, which is under pressure changes. So we add the pump, connect it. Okay, so I double click on my pump. Remember the discharge is at 100 psi, so this is my discharge pressure. Increasing it to 100 psi. Okay, so after doing this, all I just need to do is to come here and run the system. So we're going to be checking our diggers to see how the CO2 was being separated. So let's go back there and change this to diggers. Alright, so on that stream results, let's see what we have here. Let me just quickly check the mole flow. I can check the mass flow as well, depending on what I'm looking at. So I can see that my CO2, see majority of the CO2 was actually taken out of the solution. All right, so that's the product from our fermenter. It was taken, CO2 was removed over 406. Let me check it in terms of, okay, we'll get the full mole fraction. Let's check it in mass. Let's check mass flow. All right, so you can see that we removed majority of the CO2 from this process. All right, so we'll continue from here in the next video. All right, so do well to run the simulation to this point, and then we continue from here in the next video. All right.